Hey guys, welcome to Unit 6, Note C. Today we're going to talk about reaction mechanisms and activation energy, mechanics. So hopefully you've noticed by now that reactions are usually not just one step. We've talked about intermediates and the multiple steps that we can use in something maybe like Hess's law or energy cycles. So hopefully you're familiar with the idea that there could be multiple steps that lead to the final net reaction that we see when we look at a chemical equation. This is known as a reaction mechanism, where we're looking at the small steps that lead to the overall reaction. Each individual step is known as an elementary step. So a single step reaction would have only one elementary step, but a two-step reaction would have two elementary steps, or a second order reaction would have two elementary steps. Usually these individual steps cannot be observed directly, so what we're doing is really just applying what we know about the likelihood of certain reactions happening and certain behaviors of atoms and molecules and constructing a theory about how the overall reaction would proceed. What are the elementary steps? Before we look at some examples, we need to go over some vocabulary. And the first is a set of words that you need to be able to identify in the reaction. So first is our catalyst. And this is a substance, a chemical, that's going to speed up the reaction without being used up. So it should never appear in the overall reaction. It's going to be present initially, so it's going to be one of our initial reactants, but then it's going to reform as a product. So it's also going to end up in the product of the final second step. So if we look here, we see our iodide was one of our initial reactants, and it was reformed in the end in the exact same way, like the exact same ion. Nothing is different about that iodide. So the fact that it was present in the beginning and is still there at the end means that it was not used up and would not appear in the overall reaction. This would cancel out and not appear in the net reaction. So when you're asked to identify a catalyst in a mechanism, look for something that is a reactant in step 1 and a product in step 2. The next term is an intermediate. This is really what's happening at the top of our reaction mechanism graph. We've called this an activated complex and even a transition state before. The intermediate is always going to be a product of the first step and a reactant in the second step, something that's produced in the meantime but then used up right away. So in this case, it would be the IO minus that's made in step 1 but used up in step 2. And then again, this would cancel out and not appear in the net reaction. So if you're asked to identify an intermediate, look for something that is a product in step 1 and a reactant in step 2. Now let's think about how collision theory affects this. Collision theory says that particles must collide with sufficient energy in the correct orientation in order to react. So every time we have a collision that actually produces a product, that would be a single step. So each of these single events are our elementary steps. So on to some new terminology. The number of things that need to collide in order to have an effective reaction will also affect the reaction itself and how many steps that it might take to form our net reaction. The number of things that need to collide is known as the molecularity, the number of species or reactants that must participate in the reaction. So if something is unimolecular, that means that it's just a single reactant, maybe a decomposition reaction, for example. If something is bimolecular, that means we have two particles that must collide. A little bit more common. Then, as you can imagine, if we have more particles involved, it becomes less probable. So the next step would be called termolecular. Think of trace, so termolecular, 3 particles involved. And that's a little harder than letting just one thing decompose or allowing 2 things to find each other. Getting 3 things to line up, perfectly oriented with the right energy all amongst them, it's going to be a little harder. And then even more so if I have 4 or more molecules. In order for that to be the perfect collision, that's pretty dang rare and extremely remote, not really going to happen. So typically we don't assume the most complicated mechanism. kind of the idea of Occam's razor. The most simple explanation is most likely. And since we're creating a theory about how these reactions would occur, we would go with the more simple explanations, or unimolecular or bimolecular reactions. Now let's try connecting these different types of reactions to their rate law. Before we get started, there's something you should know. When we first talked about the rate law and determining the reaction order, which we would normally see in the top corner here, first order, second order, this is first order with respect to A, also first order with respect to B, we learned that you cannot determine that from the coefficients. Here's the catch. That's because most reactions do not give the rate determining step as the overall reaction. Only if the reaction happens in one step, or if I'm looking at the rate determining step only, would the rate law be able to be determined from the coefficients. So what I want to look at next is the theoretical rate law, assuming that the step that we're looking at is the rate determining step. And we'll talk a lot more about rate determining steps in just a moment. So first, looking at the unimolecular rate law, we have just one reactant. Remember, the rate law only depends on the reactants, not the products. And if that's the rate determining step, there's only one of them, then the order is 1. So the rate law is just rate equals K times the concentration of A. If it is bimolecular, it could be one of two things. Two of the same thing are combining, for example, forming a diatomic element, in which case, since I have two of the A's, the order would be second order reaction with respect to A, assuming this is precisely the rate determining step again. So now I have rate equals K times A squared. Or I could combine two different things, so I have the two separate reactants listed here. And since there's only one of each of them, then they're both first order. And so my overall rate is rate equals K times the concentration of A times the concentration of B. Moving on to some termomolecular situations, I could combine three of the same things, maybe make ozone, in which case we have A to the third power. Or I could combine two of the same things, A to the second power, but then have something different. So that concentration of that one would be to the first power. Or I could have three different things, in which case you would include all three, and they would each be to the first power with respect to its own concentration. Third order overall for each of these rate laws. And again, I cannot emphasize enough that these are the valid rate laws where the coefficients become the orders only if this is the individual rate determining step. So now let's look at an example where it is not clear yet what the rate determining step is. We're going to react the nitrogen dioxide with the carbon monoxide. And so the idea then would be, if it was the rate determining step, my rate law would be rate equals K times the concentration of NO to the first power and concentration of CO to the first power. But that's not what we have here. We have it so that it is only dependent on the NO, not the CO. So that tells me right away that this is not a one-step reaction and this is not the rate determining step. There must be more to this mechanism. And we can tell from the rate law that the reaction that determines the step would involve two nitrogen dioxide molecules as reactants, because we have NO2 as a second order. Now let's look at the elementary steps that make up this reaction. In our first step, we have the two nitrogen dioxide molecules combining to form the NO3 and the NO. And then we use the NO3, notice it was produced and then used. So we use that NO3, react it with carbon monoxide, and now form NO2 and CO2. So that would be our second step of the mechanism. First, let's take a second to identify a couple of important things. I mentioned the NO3 was produced in step 1 and used up in step 2. What's the term for that? The NO3 is our intermediate. There's something else. We have at least 1 mole of NO2 that goes into the reaction and comes out as NO2 in the end unchanged. So what do we call something that's present in the reactant side of the first step, but then product side of the second step? So that fits our definition for catalyst. Now, to be honest, it is a little weird to have a catalyst that's also present in the reaction in another place. You'd be totally justified in arguing this is more of a Le Chatelier's principle type of thing, where I'm just increasing the concentration of a reactant in order to shift the equilibrium. But technically it does fit the definition for a catalyst, and so if you were asked to identify one, then that's what I would pick. Next, I want to try to use the rate law, which I've written right down here, to try to figure out which one of these steps would be the rate determining step. Keep in mind that the rate law, where you can actually use the coefficients as the order, must be the slowest or rate determining step. So the reaction where I have the two NO2s, this first reaction, should be the one that determines the rate for this reaction. So once we get rid of our intermediate NO3, which answers this question down here, by the way, the NO3, and we get rid of the extra mole of NO2 that would cancel, our net reaction just has the NO2 and CO producing NO and CO2. We identified the first step as the rate determining step. Now the rate determining step is always the slowest step in the reaction mechanism. Think about baking a cake. It takes you a whole 2 minutes to throw together the egg and the flour and the milk, whatever goes in a cake. But maybe it takes you 2 hours to bake the cake. Well, if someone asked you how long it takes to bake the cake, you would say 2 hours. Not necessarily 2 hours and 2 minutes. The 2 minutes is negligible. So same application when we write the rate law. We write it simply based on whatever takes the most time, and we ignore the time of the other step. So since this step 2 is fast, it does not apply to the rate law. So we write our rate law based on the reactants of this very first slow step. This time we kind of solved it backwards. We were given the rate law and we were able to identify the slow step. But don't be surprised to see it the other way around, where they just tell you which step is slow and then you can identify the rate law from there, focusing on the reactants of the slow step. So basically there are 3 important rules to writing these rate laws. The first is that the sum of the elementary steps must give the overall reaction, which is something we're pretty used to from Hess's law, saying that each of the steps, step 1, step 2, step 3, must add up to the overall reaction, however many steps it takes. The thing is, the rate determining step is always the slowest step. So we need to be careful in identifying the slowest step so that we can write the rate law dependent on that step. And if you don't know which one is the slowest step, then you can't use the coefficients, which brings us back to what we learned in Notes B, where you have to come from the data. But if you do know that you have the rate determining step, if you're looking at the elementary step that produces the rate law, then the coefficients of the reactants are from the chemical equation. So that was something we said do not do in honors chem, and that was because we didn't know it was a one-step reaction. And one-step reactions are very rare. So this is only true if you have a one-step reaction or if it's just the first step that's rate determining. That's going to be what the rate law is written from. Let's focus on the rate law expressions for the 3 most common scenarios. The first one is that we have a unimolecular substance, so just one thing breaking down, in which case that's the one step, the only step. It has to be dependent on only the concentration of that reactant and be first order. That's the only way it could be. Now, if it's bimolecular, you have 2 choices. Either the rate determining step is where 2 of the same things combine, making it dependent on that concentration squared, or you have 2 different things, making it dependent on each of those things with a reaction order of 1. So this would be our rate law if we have a one-step reaction, again rare, but also if the rate determining step is the first step in the mechanism. So this is super important. It will be more complicated if it is the second step in the mechanism. Let's look at another mechanism. This time we have NO2Cl breaking down into NO and Cl. Then we have the NO2Cl reacting with Cl. So notice how we produced Cl in the first step and used it in the second step. That makes it an intermediate. And it will cancel. Notice how it's not in the final reaction. And then we're producing the nitrogen dioxide and chlorine. Notice how I produced 2 moles of nitrogen dioxide altogether. So we have 2 there. And we also used 2 of this reactant, the NO2Cl. So for my overall reaction, I'm looking at the 2NOCl producing the NO2 and the Cl, which is just basically canceling out this intermediate of the chlorine. Now that we understand the details of the mechanism itself, let's try to write a rate law based on identifying our rate determining step. Now we know the rate law should be based on only the reactants of only that slow rate determining step. So my reaction rate law will start with rate equals K, and then the concentration will be that of the reactants we just identified, which is the NO2Cl. And then since there's only one of them, and it's the first step, that's just a first order reaction, because the coefficient is the reaction order. And then since it's the only step, that makes it a first order reaction. Okay, so we've established what to do if it is the only step, or if the slow step is the first step. But what if that slow rate determining step is the second step, or even worse, the third step? Then it's not so easy. You can't just write the rate law based on only the second step, because the second step is dependent on the concentrations resultant from the first step. So to look at this, we're going to need a different mechanism, one where the slow step is the second step. So first let's look at this mechanism in and of itself. We have 2 nitrogen monoxides in the first step producing an N2O2. Then that N2O2 gets used up, so we know that makes it the intermediate. So now we have that N2O2 reacting with oxygen gas in order to form NO2. So the N2O2 is not present in the net reaction, and we have the 2 moles of NO making 2 NOs. We have the oxygen gas and then 2 NO2s. So that's the basics of our mechanism. So let's start with what we know. I want to write a rate law for the dependent step. Step 2 is the rate determining step. So if I wasn't worried about step 1, if I was only looking at step 2, I'm going to write a rate law that is just K times those reactant concentrations, and there's only 1 mole of each of them, so that would just be to the first power, or the first order for each. So something just like this. Rate equals K times the concentration of N2O2 times the concentration of O2. However, what is it that the first reaction affects? Now this goes back to our intermediate. The first reaction is producing the N2O2, so the N2O2 in the reaction rate is really not its own independent entity. It's dependent on the concentration of the reactants from the first reaction. So now think about, what if you wrote the reaction rate law for the first step? Then that would be represented as the NO squared. 2 coefficient. I have 2 of the NOs reacting in that first step. So now it's a matter of simple substitution. Since the N2O2 is dependent on the NO squared, we're going to plug in the NO squared in place of the N2O2. So here we have our final rate law. Plugging in the NO squared for the N2O2 gives rate equals K times the NO squared times the O2. To get the overall order of the reaction, we're going to add together the second order from the NO and the first order from the O for a total third order reaction altogether. The last thing that we need to cover in mechanics is all about activation energy. There's a special equation that we need to talk about, but before we get there, we'll start with some basics, the first part of which should sound very familiar. If I increase the temperature, the particles move faster, and that's going to allow for more collisions with a higher activation energy, and that's going to allow for a much faster reaction rate. So the rate constant K is very temperature dependent. There is a general rule of thumb for you to kind of get an idea of how temperature dependent it is, and that's that a 10-degree increase in the temperature will double the rate. Just in case you haven't heard this term before, a rule of thumb is not a law or a concrete formula per se, but just kind of a general guideline of what to expect. So don't try to calculate based on this rule of thumb, but you can get an idea theoretically of what's happening. Now let's touch on the Maxwell-Boltzmann distribution curves and look at how the temperature can play a role here. First of all, remember that the activation energy is basically saying the cutoff of what particles are going to have sufficient energy in order to react. So anything to the right with the higher energy would be able to react. So for example, if I added a catalyst and lower the activation energy, then I have more particles that are able to react. And so that's where we get our increased reaction rates. Now let's look at temperature's role. If I have a very large activation energy, highlighted here is the one on the right, then it really does matter what the temperature is. Look at the difference in the green versus the blue highlighted areas. The one with the lower temperature, the solid line, just has this tiny little green area here where it has those particles with sufficient energy. Compare that to our higher temperature area, the blue section, including the green, that all those particles would be able to have enough energy in order to react. That's a big difference in area. Now let's contrast that to something with a lower activation energy. So if I have less activation energy, and I can try to compare my high temperature, again under the green, and my low temperature, which was under the blue, yes, there's a difference, but that difference is not as great. So the fact that there is a lower difference indicates less of an effect of the temperature. So it's when the activation energy is large, the higher activation energy, where you have a much greater difference in area. So a greater effect on the number of particles with sufficient energy. All right, now on to the quantitative relationship between temperature, the reaction rate constant, and the activation energy. And for this, we need something called the Arrhenius Equation. So we're going to look at a formula that combines the activation energy at a certain temperature and the number of particles, or the kind of mole fraction of the reactants that have that energy. And we're going to look at that relationship to the rate constant K. So the first thing that you see here is the proportion. Remember, the alpha symbol just basically means directly proportional to. So K is proportional to E raised to the negative activation energy over RT. And the actual equation, if you use Arrhenius Constant, is that K is equal to Arrhenius Constant times this little relationship here, E raised to the negative EA over RT. So let's look at what each little factor means. Of course, you know the first one, that the lowercase k is our rate constant. But here's our new one. The capital A is our Arrhenius constant. There are a couple things you should know about the Arrhenius constant. It is unique for a specific reaction. It's not something that's the same for all reactions, but a given reaction will have a specific Arrhenius constant. Its job is basically to tell you how likely the reaction is going to occur with the correct collision theory parameters. So giving kind of a probability on the frequency. And so it's going to take into account how often, or the frequency, that you would have those successful collisions. Based on what they say here is collision geometry, we just call orientation usually, and the activation energy, or energy requirements. So basically, it's how likely those successful collisions are to occur. The units are going to be exactly the same as K because it's varying based on the exact same things. Then EA, of course, is activation energy, the same as we've seen on the graphs. R, we haven't seen in a while, but we did see once upon a time. These are our IB units for the ideal gas law constant. And then T, of course, is temperature, but again, we have seen this before. Sometimes the units are really important. In this case, T is absolute temperature, and so it must be in Kelvin. Notice that otherwise you wouldn't be able to cancel the Kelvin in the R. Now let's take a quick look at some derivations of this equation. One thing we could do is look at the natural log. So if we look at the natural log of the K1 over K2, we can set that equal to having found the natural log of e to the EA over RT is going to pull out that EA over R, so it's no longer an exponent of the E. Natural log of E just kind of goes away. And keep in mind it was over T, so if we're trying to look at how K changes with temperature, we want to keep T in the bottom, but we can look at final minus initial. So remember that K was temperature dependent, so we would be able to plug in the K for our first temperature and our K for our second temperature, and then use this to solve and see how it changes with temperature. So if you have a delta T, this would be the version of the formula that you would want to use. Next, let's go back to before we found delta T and just go back to that original equation. And if we look at just the natural log of that for this like one given temperature, you're basically getting the same thing where you have the natural log of K, just not two separate Ks. And then when you do the natural log of the E, you just pull this out of the exponent, and so it's just negative EA over RT. And then when you do the natural log, this becomes addition here, so we're adding the natural log of the A. Another way you could write that is to separate it, and this is kind of getting towards something we need to graph. We still have the ln of K on the left, and we have this negative EA over R, but we pulled out the T as something separate, keeping it in the bottom, and then we still have the plus ln of A. So all I've really done here to go from the left to the right is pull out the 1 over T, keeping in mind that the T is in the bottom. What I'm trying to get towards is identifying something I can graph in the form of y equals mx plus b. So finally, this is what our graph would look like to plot the Arrhenius data. So on the left-hand side, we have the ln of K, which is our y value. The next thing that we have is our slope, which is the negative EA over R, this part right here. And that slope, of course, would be the m in y equals mx plus b. The x-axis, of course, is our inverse temperature, so that's the 1 over T, which would represent the x in y equals mx plus b. And then the last thing we have is the y-intercept, so plus the ln of A would represent having plus b in the y equals mx plus b. So we have the y-axis being ln x, the slope being negative activation energy over R, the x-axis being the inverse temperature, and the y-intercept, the b, being the natural log of A. So we can see how this all lines up to give us something graphable. Alright guys, that does it for the end of Unit 6, Note C.